We are starting course on modern digital communication. We'll study information theory. But before starting information theory, it's important that we understand communication system in its most simplest form. If you are well aware of communication systems, what is analog communication, what is digital communication and all, then you should skip this introductory passage and you can directly go to the point where I start information theory. For others, just for 5 to 10 minutes, understand what is communication theory. See, we have in block diagram form, we have this as transmitter. What is a transmitter? Anything which emits signals, which emits messages. In communication theory, we use the term messages. So while right now I am speaking, so I am the transmitter. I am speaking something. These are messages. So this is transmitter. From transmitter, what happens? We get messages that are time dependent. Okay, the rate of change of the message per unit time. So message is a time dependent signal. For analog communication, you can say MT is, let's say, M sine omega MT. So these things you have studied. This is a transceiver. Then we have what we call channel. Channel, right now, what is the channel between someone who is viewing this video and me? I am speaking, this is air. From air, this mic is catching the signal, then it goes to the camera. From camera, there is, this is through optical communication. There are optical communications, there are copper communication channels. So channel means anything that is between the transmitter and the receiver. It can be air, it can be copper, it can be optical fibers, or combination of all. So this is transmitter, this is channel, this is receiver. This is the model. What do? We transmit the signal, it goes through the channel and is received at the receiver. If I am speaking here and someone is standing here, whatever I am saying, the person is listening. So the channel is air. But what if someone is 100 kilometers or 1000 kilometers away from me? Then whatever energy I put into my voice cannot reach that person. Then we'll have to use certain channels so that my message goes to that point. What we'll do? We use modulation techniques. Why? To suit the channel. Now, what is modulation technique? Modulation technique means altering the signal according to the carrier signal. We have another signal that is capable of taking this, your transmitting from here to, and it reaches this. That is from transmitter to receiver, that carrier signal is able to travel. And we put our message signal over that carrier signal. Let's say we have a signal that is capable of traveling this distance, whatever is the distance. This is carrier signal. And what we do, we put our message signal over this. Like a bus is going from this station to this station. We sit on the bus and we are transported to this point. Similarly, we have message transported through the carrier signal. So this process is called, and how we actually do that? For example, if we ride a bus, there are seats. We go and sit on seats. We sit on seat and then we are transported. Similarly, some property of the carrier signal is modulated or altered according to the message signal, and at the receiver that alteration is captured and the message signal is recreated. This process is called modulation. For example, you must have studied amplitude modulation, frequency modulation. What we do? We modulate the amplitude of the carrier signal according to the message signal. Then it reaches here, and at this point what we do, we take the amplitude and remodulate it. Okay, so what we do, at the receiver point, the modulated signal is taken back, retrieved back, and we get the original signal. So this is modulation technique. We have analog modulation techniques such as amplitude modulation and frequency modulation. Then in digital communication, we have a very very popular term that is called pulse code modulation. We use pulse code modulation in for transmitting digital signals. Then there's another technique. What I discussed just now was modulation. You can go to individual topics and see the details if you have any confusion. I'm just giving you a gist of what we have already learned. Then second thing is that is called multiplexing. Multiplexing. What is multiplexing? See, we have, let's say this channel is a copper cable. We can transmit more than one message signal. That is, I'm rubbing this. Okay. Let's say we have multiple signals, M1, M2 and so on. And these can be intertwined in a single signal and sent to the receiver. These are different signals. And at the receiver end also, we have a demultiplexer, which, let's say this is a demultiplexer. It then again recreates a different signal. Okay. For example, 50 passengers can sit on a bus and they can travel from one place to another, and then again they get down the bus and go to their respective places. Similarly, we have these multiplexing and demultiplexing techniques. There are so many digital and analog multiplexing and demultiplexing techniques that you must have already studied. Now, the important thing that I wanted to explain at this point, which is required in information theory, is called the noise. Where do we have noise? Noise, we can have noise in the transmitter, but whatever comes out of the transmitter, that is our message. So we are not concerned with that noise. That noise, the noise that is generated in the transmitter and all, that is another topic that is dealt separately. We minimize the noise and all. Let's say we have pure messages. Then noise is generated and is added in the signal when it passes through the channel. This is the biggest or the most important limiting factor for communication or in communication. That is, our transmitting capacity through a channel is limited by the noise. Initially, when we were using analog communication, starting itself, analog communication we were using, the multiplexing was very low. That is, very few channels could be multiplexed in a single channel. Then techniques evolved and we were able to multiplex more and more messages in a single carrier signal. But everywhere the issue is that noise actually limits the transmission of signals. How much signal can be transmitted over a single channel is actually limited by the noise. Okay. Now I am getting into information theory. These things you have studied, or if you have, it's not in your mind, you should go and revise. Now I am starting with information theory. Okay. So you understand noise in a channel. Now noise actually leads to errors in digital communication. If you have noise and you lose a signal, you lose a bit, that is error. So noise leads to error. So in terms of digital communication, we say that it is not possible to achieve error-free communication. Or what I said about noise, I can say that because of error or the data transfer rate, that is from transmitter to receiver, the data transfer rate is actually limited by noise. Okay. Now let me explain this. Let's say the probability of error is PE. When we are transmitting a signal, when we are emitting messages, let's say M1, M2 and so on. Let's say the probability of error associated with a message is PE. Undoubtedly, you understand, if this is very less, or if this tends to 0, the probability of error tends to 0, it means we can achieve noise-free transmission. noise free communication. Transmission and receiving is communication, so we can achieve noise free communication. But we know that this is related to or proportional to e to the power minus, let's say this is a constant, and this EB, that is energy per bit. When we are talking of digital communication, it's in binary digit, that is bits. So EB is energy per bit, and our probability of error is actually proportional to e to the power minus k EB. Now from here you can understand that if EB tends to infinity, that is if this is very large, EB is very large, that is energy per bit. If we increase energy per bit in transmission to a largest, to a very big number, this would imply PE tends to 0. Okay, that is if you increase the energy of the signal that is to be transmitted, then your probability of error will be reduced to 0, will tend to 0. But is it possible to increase the energy per bit to infinite levels? No, obviously not. Let's see it mathematically. SI, that is the signal power, is given as EB into RB. We'll study these things later on. This is just for introduction so that you understand what we are going to study. This is what? Signal power. Signal power is equal to energy per bit into rate of transfer, data transfer per bit, EB into RB. Now, if you increase energy per bit, how can you increase energy per bit? By increasing, see, this is EB is therefore proportional to SI and inversely proportional to RB. So there are two ways. First is you keep on increasing the signal power, 100 watts, 1000 watts, 1 megawatt. This is the first way, which is obviously not possible practically because you have circuitry, you have your system, and that system actually limits the power transfer rate, energy. You cannot put 1 megawatt of power in a small transmitter. So, and it is also not economical to put so much energy. So there's a limit to increase of signal power. Then second way is to reduce transfer rate. That is, if the transfer rate is 1 mega bits per second, reduce it to 1 kilobit per second. This is also undesirable. But for the time being, EB is directly proportional to SI and EB is inversely proportional to RB. So that if you decrease data transfer rate, your energy per bit will increase, and this increase in energy per bit will actually lower down your probability of error. Okay, so this means to achieve from these equations, we understand that to increase to make the probability of error 0, the only possibility is to increase EB, that is energy per bit, to infinite levels, and that is possible only when you reduce the data transfer rate to almost 0. So both things are, or this thing is not desirable. Here what we got was Shannon's theorem. We'll study it in detail later on, but for the time being you should understand what is Shannon's theorem. Shannon's theorem defined a term that is called channel capacity, and according to this theorem, if the data transfer rate, this is kept below the channel capacity, then we can have P equal to 0. That is, our probability of error will be 0. That is, we'll achieve error free communication, digital communication, if the data transfer rate is kept below the channel capacity. Clear? So this is all about your information theory, what we will be studying. So if this is clear, now I'll explain, or I'll introduce to you what is information and what is entropy. Okay. Now let's understand what is information. See, information is related to uncertainty, it is related to surprise, and it is related to the probability of occurrence of an event. How? Let me explain. Let's say this is east, this is east, obviously this is west, and when this is east, this will be north. Now I have three statements. First is, tomorrow the sun will rise in the east. Okay. Second is, tomorrow the sun will rise a little in the little north to east at this point. And the third statement is, tomorrow the sun will rise in west. First statement is, the sun will rise in east, the eastern direction. The second statement is, sun will rise a little, let's say northern to the actual eastern direction. And third is, the sun will rise in the west direction. Now this has no information. The sun will rise in the eastern direction because we know sun rise in the east. There is no uncertainty to it. This is certain that sun will rise in the east direction. That is, there is no element of uncertainty or surprise in the first statement. And I'm writing no uncertainty. No uncertainty. That is, probability of occurrence is 0. Sorry, probability of occurrence is 1. It is certain that sun will rise in the east direction. Here, there is very little uncertainty and probability is almost equal to 1, near 1, maybe 0 0.9, 0 0.98, 0 0.97. Here, this is completely uncertain. This is very surprise. If you take out today's newspaper and it's written the sun will rise in the west tomorrow, you'll be surprised how this is possible. So this has uncertainty, this is a surprise, and probability of occurrence is 0 here. We know this cannot happen. So probability of when probability of occurrence of an event is 0, it is very uncertain. It is almost, not almost, it is uncertain, and it has the greatest surprise for you. Now from here we understand that, again I'm going to this point. No uncertainty, probability is 1. What is information? 0. Here information is 0. No information. Sun will rise in the east. What is information? What information do you get from this? Nothing. But when you say sun will rise in the west, it is uncertain. This is a surprise. Probability is 0. But information here is high. Very high. That is, from here you can intuitively you can understand that information is inversely proportionate to probability. This is clear, that when the probability is high, information will be low, and when the probability is low, information is very high. Clear? So this we have understood from this discussion. Now let's go to the next point. What is the mathematical expression between I and P? It is log of 1 by P. For any number system, may it be decimal, it be binary, this formula holds. But in digital communication, we deal with binary system. So this is usually this. If we are dealing with some other system, we can convert it to that part. Log r base 2 into that, if r is the base of that system. So this is the formula in binary system which represents the relation between information and probability. So if the probability in a message is P, its information mathematically is log 1 by P base 2 for binary system. Clear? In engineering terms, the more probability a function, a message has, the lesser time it will take to get transmitted. That is, time is again inversely proportional to probability. That is, when probability is high, it will take less time, and when probability is low, it will take more time. And our concern is only time, because we are saying data transfer rate, the rate at which we are able to transfer data. Clear? So I equal to log 1 by P is the formula for any system. For binary, it is log base 2. Keep this in mind, and then we will now understand what is entropy. Let's say we have M1, M2, M3 and so on up to Mn messages, n number of messages with probabilities P1, P2, P3, Pn. Okay. Let's say what is I small I, for any I can be from 1 to n. So I can be written as we just saw, it was log of 1 by, let's say, P of I, this is II. So we now define a term entropy of a source. Why source? Because we are getting messages from from the source. So entropy of a, we have one more term here, memoryless source. What is the meaning of memoryless source? Memoryless source means that this message is independent of this message. This message is independent of this message. That is, the messages are independent of each other. Any message is not related to its preceding or succeeding message. That is called a memoryless source. So entropy of a memoryless source is nothing but average information per message. So average information per message, this is the definition of entropy of a source, and it is given by I equal to 1 to n. We have Pi into II. You know how to take average? We have seen this in statistics. So this is I equal to 1 to n Pi into II. Clear? I am just rubbing this. So entropy is denoted as this HM. So HM is defined as, actually, I equal to 1 to n, it is the average information per message, so it becomes Pi into II. But you have seen what is II? It is log 1 by Pi. So we can write it like this, I equal to 1 to n Pi into log 1 by Pi. Now log 1 by Pi can be written as minus log Pi, log 1 minus log Pi. So this actually comes to minus I equal to 1 to n Pi log Pi. Okay. So you should learn this formula. This is for entropy, that is average information per message is called the entropy of the source, and for a memoryless source, entropy is equal to this. Now another term for equiprobable messages, that is, we just saw we had M1, M2, M3 with probability P1, P2, P3 and so on. Equiprobable messages means that the probability of each message is same, that is P1 is equal to P2, that is equal to P3 and so up to Pn. So in that case, you know, the probability will be 1 by n of each message. Probability of each message will be 1 by n when these all are equal. So if you put in this equation H for, let's say I'm writing M1 for equiprobable, or ME, that is equiprobable messages, this will become minus 1 by n log 1 by n. If you take it from I equal to 1 to n, it simply comes to log n. Okay. So the entropy of a source which emits equiprobable messages that are memoryless, if we have n messages, then the entropy will be log n. Clear? So this concept should be kept in mind. I'll give some examples later on to understand it, or even without examples also you can understand this. If you are given n, if you are given Pi and all, you can solve it, but later on we'll see examples also. Okay, clear up to this?